Hi, my name is Dr. Habib Ahmed and I work at the Center for Advanced Electronics and Photovoltaic Engineering at International Islamic University, Islamabad. In the previous video that I posted on my YouTube channel, I showed you how to perform the simulation of ion implantation using the SUSPRE software, where SUSPRE stands for stopping and range of ions in matter, and TRIM stands for transport of ions in matter. TRIM is the older version of the software. It was originally introduced in 1980s and later it was renamed to SUSPRE. Today I'm going to tell you about another software for the simulation of ion implantation in various materials using different dopants. The name of this software is SUSPRE and it stands for Surrey University Sputter Profile from Energy Deposition. Just like the SUSPRE and TRIM software, the SUSPRE software was also introduced in 1980s, and this basically is an ion implantation calculator. SUSPRE has been found to be in good agreement with the SUSPRE and TRIM software, and it has also been found to be in good agreement with the experimental studies as well. Now, SUSPRE is not exactly as accurate as the SUSPRE and TRIM software, but is still in good agreement with this software. However, one of the biggest advantages of the SUSPRE software is that it is much faster as compared to the SUSPRE software. It only takes seconds to perform the simulation of ion implantation using the SUSPRE and TRIM software. Another advantage of the SUSPRE software as compared to the SUSPRE and TRIM software is that in SUSPRE we can also introduce dose per centimeter square, which eventually tells us about the carrier concentration in different materials for different dopants. In SUSPRE and TRIM software, we can introduce the species or the dopants, and we can also mention its energies, but we cannot include the dose in SUSPRE and TRIM software. So this is one of the biggest advantages of SUSPRE as compared to SUSPRE and TRIM software. First, it is faster. Secondly, we can introduce dose as well in SUSPRE software. SUSPRE software is mainly used for quick calculation of range, damage profiles, carrier concentration, and electronic and nuclear stopping for ion implantation. In today's video, first I'm going to tell you how to install the SUSPRE software. Secondly, I'm going to focus on a few basics of ion implantation. And later, I'm going to perform the simulation of ion implantation in SUSPRE software. And somewhere in the middle, I'm also going to perform a comparison of SUSPRE versus the SUSPRE and TRIM software so that you can see how we navigate through both these softwares. So let us start with the first task, and that is how to install the SUSPRE software. For that purpose, here is the link for downloading the software. I'm going to post and pin this link in the video as well, in the comment section of the video. And once you get to this link, just click on install. It's going to download the software for us, and then we click on setup.exe. Over here we click on more info, and then I trust this software, so I click on run anyway. And here, after a couple of really simple steps, the software is going to be installed. So post installation, I look for the software in search. We have the software over here, just click on it. It's taking some time to open. Generally it does not take that long, but right now it's taking a little bit of time. So in the meantime, I'm gonna tell you about a few basics of ion implantation. Ion implantation is a low temperature technique for the introduction of impurities into semiconductors. And here is the block diagram of ion implantation. The first thing that we need is a source of ions. How do we get the source of ions? For that purpose, we introduce a low pressure gas into a tube which has two electrodes, a cathode and an anode. Then we apply voltage to the electrodes and keep increasing the voltage until we get to a point where the voltage exceeds a certain value, and we call that value the striking voltage. At the striking voltage, ionization of the gas occurs, leading to plasma, where plasma is a combination of electrons, neutral atoms and molecules, and ions. And the color of different kinds of plasmas is different. So once the plasma is generated, it glows with a certain color. For example, oxygen gives us light blue kind of plasma, while argon gives us bluish pink, more like violet or purplish kind of plasma. Once the plasma is generated, we pump that plasma and let it pass through an analyzing magnet, and this analyzing magnet actually works as a mass separator. It's going to allow only the intended ions to deflect at a certain angle and then pass through, resolving aperture. And then we accelerate these ions at certain energy levels. We focus them so that they hit at different x and y coordinates of the wafer. So that is how the process works. Then I'm going to skip some slides and just focus on the essentials. So assume that we want to implant ions into a silicon substrate, and assume this is the direction of the ion implantation. So these ions are going to strike the surface of the silicon substrate at certain energy levels. These energy levels are in kilo electron volts to mega electron volts range. Depending on the energy of these ions, they travel down to a certain depth inside the substrate, resulting in distribution of these ions in the horizontal direction and also in the vertical direction. The higher the energy of these ions, the more they travel inside the silicon substrate. So initially they have like energies in hundreds of kilo electron volts, and once they strike the surface of this silicon substrate, they keep losing energy. They encounter electronic and nuclear energy losses, and eventually they lose almost all of their energies and get down to almost thermal energy at room temperature, which is of the order of 25 to 26 milli-electron volts, resulting in eventual stopping of these ions. Now there are two mechanisms responsible for the ion implantation energy loss. The first one is nuclear stopping, in which the ions they encounter positively charged nuclei, and nuclear stopping occurs mostly in heavy atoms, resulting in more damage to the substrate or to the host atoms. The second type of ion implantation energy loss mechanism is called the electronic stopping. In electronic stopping, these positively charged ions are actually slowed down by clouds of electrons, resulting in excitation of electrons, further resulting in some sort of heat. So electronic stopping is more observed in lighter atoms, for example hydrogen or boron, while nuclear stopping is observed in heavier dopants, for example phosphorus or for example arsenic. Lighter atoms travel deeper inside the substrate or the host material, while heavier ions travel shallower into the substrate or the host material. And this concept is crucial. And by the way, ion implantation introduces some sort of damage to the host material. So after ion implantation, we need to perform annealing to recover from that damage. Here are the ion implantation parameters. The first one is ion species. For example, if we want to perform p-type doping of silicon, we need to use either boron or aluminum as a dopant. Similarly, if we want to perform n-type doping of silicon, for that purpose we need either phosphorus or arsenic as a dopant material. The second parameter is ion energy. It's in the range of 5 kilo electron volts to 10 mega electron volts. Ion energy defines the depth of ion implantation inside the host material. The higher the energy, the deeper these ions can travel inside the substrate or the host material. And the third parameter is implant dose in the range of 10 to the power of 12 to 10 to the power of 16 per centimeter square. Implant dose defines the carrier concentration of the dopants inside the host material. Now, ion implantation results in Gaussian distribution with respect to depth for the dopants. For example, assume that we are performing ion implantation at this point over here. Now, as these ions travel deeper inside the substrate material, they get scattered in different directions. They have a peak concentration at some point, for example, over here. And this peak concentration defines the range of ion implantation. And then they have uncertainty along the direction of the ion implantation, which is called projected straggle, represented with delta Rp. Similarly, they also have distribution in the lateral direction, and this lateral distribution is called transverse straggle. That's pretty much it for the theory part. Now let us focus on the software. So the software interface is now open. Assume that I want to perform boron implantation of silicon. So here is the target material or the host material, and in order to include the host material over here, I left click in this tab. It leads me to the periodic table, and then in the periodic table I click on silicon, so it includes silicon material as a host material or as a target material. And since I'm gonna perform boron ion implantation of silicon, so the ion details are given in this window. So I just left click over here in this tab. Once again, it leads me to the periodic table, and in the periodic table I click on boron. So it automatically picks the parameters for boron, for example, the atomic number, the atomic mass, etc. Now, I have to define the energy and the dose. Fluence, by the way, represents dose for the ions. So initially, I'm going to set the energy to 250 kilo electron volts. And let me set the dose to 10 into 10 to the power of 14 ions per centimeter square, or you can also say 10 to the power of 15 ions per centimeter square. The angle of incidence, you have control over the angle of incidence, but I'm gonna set it to 0, and then you can also enter the beam current. So as I already mentioned, that one of the advantages of SUSPRE as compared to the SRIM and TRIM software is that in SUSPRE we can introduce dose as well, which eventually leads to the carrier concentration. Now we have introduced the three most important parameters of ion implantation, which are, once again, let me get you to that slide, which mentions the important parameters for ion implantation. The species, ion energy, and implant dose. The species is boron. Energy we have set to 250 kilo electron volts, and I have set the dose to 10 to the power of 15 per centimeter square. We can also enter the plot depth, and its unit is angstrom. So I assume that I want to see the profile of the ion implantation down to approximately 1.5 micrometers. So that would be 1500 nanometers, or you can say 15,000 angstroms. And in order to look at the results, I click on new, and right away it gets me to the results. So in these results, you can see the carrier concentration over here. The peak carrier concentration is approximately 3 into 10 to the power of 19 per centimeter cube. Similarly, we can also see the damage or the disorder, and the damage, the peak damage we see is around this value, which is around slightly less than 6,000 angstroms, or we can say 600 nanometers or 0.6 micrometers. Similarly, we can also see the mean range or the projected range, which is around 728 nanometers. And also, since boron is a lighter material, we already discussed that lighter materials encounter electronic stopping or electronic energy loss. So this orange color over here represents electronic energy deposition or electronic energy loss. And similarly, the nuclear deposition is represented by the red curve. So since boron is a lighter dopant, it's going to encounter more electronic energy loss as compared to nuclear energy loss. So that point is also clear over here. Also, we can look at similar results in the SRIM and TRIM software as well. And I already posted a video on that, so I'm just gonna go to the software and run the SRIM and TRIM software. Click on TRIM calculation, and I want to perform boron implantation of silicon material at an energy level of 250 kilo electron volts, and I want to look at a depth of 15,000 angstrom. and then further we can enter the number of ions for the simulation purpose. If I define more number of ions, the simulation is going to take forever. So I'm going to enter 500, and this window is for autosave at ion number, so I can set it to 250. Then I want to look at ion ranges, backscattered ions, sputtered ions, and collision details. And I can click this one as well. Okay. Click on Save Input and Run Trim in order to run the simulation. And we can look at the progress of the simulation and runtime as well over here. So we are at ion number approximately 130 right now, and it's going to go up to 500. Okay, I want to look at the ion distribution, and the ion range over here from trim is approximately 684 nanometers, while from the SUSPRE software our range came out to be approximately 728 nanometers. So there is still some variation in the results of these two softwares. They are not exactly the same, but they are close enough. And I can look at the damage events as well. The peak damage occurs at approximately, I would say, going by a rough guess over here, at approximately 600 nanometers, which is also visible in the SUSPRE software as well, where we see peak damage around 600 nanometers. However, the resulting range is not the same in the two software. We can also look at ionization, energy to recoils, ion distribution, collision details, etc., and some other parameters. But anyhow, I just wanted to show you how, a comparison of simulation of ion implantation in the SUSPRE software and also in the SRIM and TRIM software. And as you can see there, the SUSPRE software runs faster as compared to the SRIM and TRIM software. And also we have the control over the dose of ion implantation in the SUSPRE software as well. In the TRIM software we don't have control. Here is the window where we enter all the input parameters, and we can introduce the species, and also we can enter the energy of the ion implantation, but we cannot enter the dose in the SRIM and TRIM software. However, the results of SRIM and TRIM software are slightly more accurate as compared to the SUSPRE software. So at this point I'm going to close the SRIM and TRIM software. We do not need it anymore. And from this point onwards I'm just going to focus on the SUSPRE software. So from these input parameters, the species is boron, the energy is 250 kilo electron volts, and the dose is 1 into 10 to the power of 15 per centimeter square. And our carrier concentration came out to be around 3 into 10 to the power of 19 per centimeter cube. Now let us play around with the input parameters. For example, first of all, I want to change the carrier concentration, not the carrier concentration, the dose from 10 to the power of 15 to 10 to the power of 14 per centimeter square. So let us see what happens to the carrier concentration. In order to run the simulation once again, I click on New. And now you see that the peak carrier concentration around 728 nanometers is 0.3 into 10 to the power of 19 per centimeter cube. So by decreasing the dose from 10 to the power of 15 to 10 to the power of 14 per centimeter square, our carrier concentration has reduced from 3 into 10 to the power of 19 per centimeter cube to 3 into 10 to the power of 18 per centimeter cube. So a 1 order of magnitude decrease in the dose results in a 1 order of magnitude decrease in the carrier concentration. Now let me set the dose back to 10 to the power of 15 per centimeter square, and I click on New once again. So now it has reset the concentration to 3 into 10 to the power of 19 per centimeter cube. And now I want to play around with the energy level to see the effect of that on the peak carrier concentration and also on the damage or disorder by the ions inside the material. So let me set the energy to 100 kilo electron volts, and then I click on New once again. So now we see that the peak carrier concentration is now at 342 nanometers. We can see the mean range or the projected range over here. It's 3421 angstrom, or we can say 342 nanometers. Also, the peak disorder is now at around 250 nanometers. So by decreasing the energy, we actually let the ions to travel shallower into the material, and we observe the peak carrier concentration at around 300 nanometers, 342 nanometers at 100 kilo electron volts, as compared to 700 plus nanometers at an energy level of 250 kilo electron volts. Now let us see what happens if I reduce it further to 10 kilo electron volts. Click on New once again. So now you can see that the disorder is now peaked at the surface, and also the peak carrier concentration is observed at 38 nanometers. Let me set the energy level to 250 kilo electron volts. And now I want to introduce another dopant into this material. I mean a different dopant into this material. So first focus on the results once again. When my species is boron at an energy level of 250 kilo electron volts and dose of 10 to the power of 15 ions per centimeter square, I see a peak carrier concentration at 728 nanometers and a disorder around 600 nanometers. And since boron is a lighter dopant, electron stopping or electronic energy loss is dominant as compared to the nuclear energy loss. Now I want to dope it, for example, N-type. And for N-type doping, let me introduce arsenic, which is a heavier material as compared to boron. So all the other parameters are going to remain the same. I just want to change the species or the dopant. And let me introduce arsenic now, which is a heavier dopant, and see what happens to its peak carrier concentration, its projected range, its damage profile, and to its electronic and nuclear stopping or electronic and nuclear energy loss. So I clicked on arsenic, and then I click on new. So now we see that the peak carrier concentration is now at 158 nanometers. As compared to the lighter material, our projected range has decreased from plus 700 plus nanometers to 158 nanometers. And also we see the peak disorder at the surface of the material, or we can say at the surface of the substrate or the wafer. Also, since arsenic is a heavier dopant as compared to boron, now we have more nuclear energy loss as compared to the electronic energy loss. And also, in case of boron doping of silicon, we observed a range of 700 plus nanometers. So in case of arsenic doping of silicon, now the range has reduced to 158 nanometers. It also clarifies our point that lighter atoms travel deeper into the host material, while heavier ions travel shallower into the host material or into the substrate. We can also perform compound ion implantation, like for example here first I've added arsenic into the substrate material, which is silicon, and sometimes we need p-n junctions. So first we can introduce arsenic doping into the silicon, and then we can also introduce boron into the silicon material. So for that purpose, for compound ion implantation, I click on boron. And since I want to add 2 layers, the arsenic ion implantation is already added. On top of that, I want to add boron ion implantation. So I clicked on boron and I click on add to add another layer of ion implantation. And now we can see in the results that this peak is for arsenic doping of silicon, and the peak is observed at 10 into 10 to the power of 19 per centimeter cube for arsenic doping of silicon. And the second peak over here is for boron doping of silicon, which is observed at around 728 nanometers at peak carrier concentration of 3 into 10 to the power of 19 per centimeter cube. So up to approximately this point, up to approximately 300 nanometers of the host material, we will have n-type doping, and then from 300 to approximately 1200 nanometers or 0.3 micrometers to 120 micrometers, 0.3 to 1.2 micrometers, we will have p-type doping of the substrate. We can also make a p-n junction out of this. Similarly, we see 2 peaks for the damage profiles as well. This one for the arsenic ion implantation, and the second peak for boron ion implantation. We can also perform ion implantation for compound materials using the SUSPRE software. For example, assume I want to perform ion implantation of gallium nitride. For gallium nitride, we know that silicon and germanium act as an n-type dopant, and magnesium acts as a p-type dopant. So let me first perform the germanium ion implantation of gallium nitride. In order to select gallium nitride, I click on select compound from the table. It stopped responding, so I'm going to close it and open the program once again. Okay, I'm going to go to SUSPRE once again. And it's going to take some time to open. In the meantime, while it is still opening, there is a previous older version of SUSPRE software as well, and I can show you the interface of that. So here is the older version of the SUSPRE software, and over here, for example, if I want to perform the boron ion implantation of silicon, I click on boron, drag it to this tab, and the host material or target material is silicon, so I click on silicon and drag it to this tab. I define the energy level. For example, I set it to 250 kilo electron volts, and I set the dose to 10 to the power of 15. Then I also have control over the depth. Let me set the depth to 15,000 angstrom or 1.5 micrometer. And then I click on new, and it gives me all the output parameters. Then I have control over checking some parameters, like I want to look at some parameters, not all the parameters. So on the right axis we have disorder, on the left axis we have carrier concentration per centimeter cube, represented by the black trace, and the blue trace represents the disorder versus depth. So this is how the older version works. The newer version is also open now, and I wanted to show you how to perform the ion implantation of compound semiconductors. So in order to first add the host material, I click on compound from table, for some reason it's taking time once again. While it's working on that, let me try it on the older version. So in the older version, I click on pick compound, and for example, I want to include gallium nitride, so I click on OK. And then for the dopant, let me first try magnesium doping of gallium nitride at an energy level of 250 and dose of 10 to the power of 15. And I want to plot it up down to, I would say, 1 micrometer or 10,000 angstrom. And then I run the simulation, so I click on new. So here is the carrier concentration represented by the black trace and the disorder represented by the blue trace. So the peak carrier concentration is observed at a range of 271 nanometers, while here we see the peak disorder. Similarly, we can add an N-type dopant layer to the gallium nitride material, and for that purpose we can use silicon or germanium. I'm going to use germanium over here, and instead of clicking new, I click on add to, because I want to add 2 ion implantations into the gallium nitride material. So now it gives me profile for compound ion implantation of the gallium nitride material, where up to this point from the left I observe N-type doping, and from this point onwards I observe the P-type doping. One advantage of the newer version as compared to the older version is that in the newer version we can save the results in Excel file as well. Well, in the older version you can just save the images. So let me go back to the newer version once again, and for some reason the select compound from the table is not working right now, but I have previously tried it. Maybe it's because of the double installations. I had previously installed the software on my computer, and I tried to install it once again, so maybe it might have some conflict with the previous version. But anyhow, I want to show you how to save the results. So let me do that for boron doping of silicon at energy level of 250, the value that we have used so far, 250 kilo electron volts, and let me set the depth to 15,000 angstrom or 150 nanometers, and then I click on new. So it gives me the results. In order to save the results, you go to File, Export CSV, and then I can set the path, and let me save it as boron doping of silicon at desktop. So here you can see the results in Excel format. So here you have a column for depth, and then implant ions, nuclear energy loss, electronic energy loss, damage, and the resultant carrier concentration is a function of depth. So then you can plot them in Origin or some other software for in order to achieve better plots for publication purpose. I'm going to close this file, and I'm gonna give one last try to select compound from the table. Oh, it's working now. Great. So from here I'm gonna select gallium nitride. So I double clicked on gallium nitride, and I want to perform magnesium ion implantation of gallium nitride at energy level of 250 kilo electron volts and dose of 10 to the power of 15 per centimeter square. Everything is all set, so I just click on new. Yeah, it's over here. Okay, and then if I want to add another layer of germanium doping of gallium nitride, I can do that as well, and click on add to add this second layer of ion implantation. And as you can see, the profiles are limited down to approximately a depth of 6,000 nanometers. So instead of setting the depth 6,000 angstrom, my bad, instead of that to 6,000 angstrom or 600 nanometers, and then click on add once again. So now the results are plotted down to 6,000 angstrom. By the way, I have to subtract it because I think I added 2 layers of germanium instead of 1 layer of germanium. Yeah, so now it's working. Like even in this one, I see that we can limit it to, in fact, 3,000 as well. So once again, I'm going to add it and subtract it. Okay, so you see the profiles over here. So this is how the SUSPRE software works. I hope this session was useful for you, especially in the field of nanotechnology, where we perform different processes Ion implantation is one of the crucial processes. So I thought to give a perspective of the simulation of ion implantation on SUSPRE software as well as the SRIM and TRIM software for better utilization. And I hope this session was informative for you. Take care, and I will talk to you next time. Bye.